Hello everyone, welcome back to our Python series. Up until now, we focused purely on making our code work. Today, we are unlocking a major software engineering milestone, moving from code that just works to code that works efficiently. If you ever want to write software for things like self-driving cars, ride-sharing systems, or algorithmic trading desks, you have to understand how your code behaves at scale. Our code philosophy for this module remains simple. Programmers are made, not born. You learn by doing, which is why we'll be spending our time breaking down these concepts directly inside our notebook. Today's big question is, how does my code slow down as my data grows? Let's jump into the slides and look at a simple game. Imagine a friend thinks of a number between 1 and 100. Every time you make a guess, they'll tell you if you are correct, too high or too low. How many guesses do you actually need to find the number? If you use the most basic strategy, guessing 1, then 2, then 3, all the way to 100, this is called linear search. In the absolute worst case scenario, if the number is 100, you have to make 100 guesses. It works, but it's slow. Let's look at how we write this in Python. Here is our linear search function. When the code is on the screen, watch what it's doing. It takes a list A and target value X. It uses a basic for loop to inspect every single element sequentially. If an element matches X, it immediately stops and returns true. If the loop completely finishes and finds nothing, it returns false. Now, how do we evaluate if this algorithm is good? If X is the very first element in the list, the program finishes instantly, and that's our best case. But as computer scientists, we focus heavily on the worst case analysis because it gives us an upper bound on performance. For a list of size n, the worst case means stepping through all n items. Because the number of operation steps grows in a direct straight line alongside the size of our input, we classify linear search as having a time complexity of O(n) or linear time.
Let's understand big O notation in Python. This loop runs in linear time. Its performance is described by O(n). This helps us write better code.
But what if we know ahead of time that our list is already sorted? We can use a much faster recipe called binary search. Look at the code on the screen. We establish a tracking window with two pointers, low at index 0 and high at the end of the list. Inside our while loop, we calculate a midpoint to cut the list roughly in half. We look at the value of that midpoint. If it equals a target x, we win and return true. If our guess is too high, we throw away the right half of the list by moving our high pointer down. If it's too low, we throw away the left half by moving the low pointer up. We repeat this until the pointers cross.
This is how binary search works. It finds a target in a sorted list. First, we check the middle element. We eliminate the half we don't need, and quickly find our target value.
Think of the power of this strategy. Every time the loop runs, we discard exactly half of the remaining numbers. This is where logarithm comes in. A logarithm is simply the inverse of an exponential. It asks how many times do we divide the number by 2 to get down to 1. For a list of size n, the worst case will never take more than log n to the base 2 steps. This makes binary search incredibly fast, earning it a complexity rating of O log n or logarithmic time. At this point, you might ask, why don't we just use a stopwatch to see how fast our code runs? Because wall clock time changes based on your computer's processing speed, your implementation language, and background tasks. Instead, we count basic computational steps, arithmetic operations, comparisons, assignments, and memory access. When we analyze these steps, we always ignore constant multipliers and lower order terms. For instance, if an algorithm takes 5n plus 2 total steps, as n grows towards a million or billion, that plus 2 becomes completely meaningless. And the multiplier phi doesn't alter the code trend line. We only care about the highest order of growth for massive inputs. Here is the baseline scale of standard runtime growth rates we use to classify the code efficiency. O1 is constant time. O log n is logarithmic time. This is highly efficient and scales beautifully, for example binary search. On is linear time, scales in perfect direct line with size, for example linear search. O n log n is log linear time. This is typical bound for efficient sorting routines. On squared is quadratic time. Performance degrades quickly with large data, for example nested loops. On factorial is factorial time. explodes catastrophically. Example, traveling salesman problem.
Let's explore Big O notation. It shows how algorithms scale. We can visualize this on a graph. O1 means constant time, never changing. On is linear, growing with input. Quadratic time often comes from nested loops. Logarithmic time is highly efficient for large datasets. O of n log n is typical for sorting. Now you understand Big O scaling.
Now that we know binary search is superior to linear search, should we always sort an unsorted list before searching it? If you're only going to sort through a list for a single time, sorting it actually takes more effort than simply running a raw linear search. But if you have a dataset that you intend to search multiple times, paying the upfront cost of sort gives us dividends over time. Let's head over to the notebook to build our first sorting tool. Let's start with a straightforward sorting method, selection sort. Look at the code on your screen. The strategy here divides our list into a sorted section in the front and an unsorted section at the back. In our outer loop, we section through each index position of the list one by one. For each position, our inner helper function findMinIndex scans the remaining unsorted section to find the smallest elements available. Once found, we swap the minimum element right into our current outer index position. We repeat this process until the entire list is sorted. While selection sort is very intuitive to read and write, it has a serious performance flaw. Because it runs an outer loop n times and for every step it must scan the rest of the list using an inner loop, it relies on nested iterations. This means its running time scales quadratically, giving selection sort the worst time complexity of O(n) squared. It works fine for small arrays, but it quickly slows down on larger datasets. To do better, we must shift our strategy to a recursive divide and conquer approach called merge sort. Look closely at the code on the screen to see how recursion completely shifts this paradigm. Our base case states that if a list has length of 1 or 0, it is already inherently sorted, so we return it immediately. For longer lists, we find the middle index and slice the list clean in half. We then recursively call merge sort on both separate halves. Once those sublists are sorted down at the base layers, our merge subroutine combines them back together. It compares the front element of both lists, pushes the smaller elements into the result array, and slides its pointer forward. Once the side runs dry, it appends the remaining item from the other side.
This is how merge sort works. It uses a divide and conquer approach. First, we divide the list into equal halves. Then, we merge them back in the correct order. And now our list is perfectly sorted.
Why is this so much more efficient? Splitting our array in half repeatedly takes logarithmic time or log n stages. At each of these individual stages, merging the element back together requires a single linear pass of O(n) steps. When you multiply these together, merge sort achieves a total time complexity of O(n) log n. This is a massive speedup over selection sort of O(n) squares complexity, especially when your data scales up to thousands or millions of elements. Understanding computational complexity changes the way you look at code. You stop just trying to get a green check mark and start thinking about scale, resource limits, and system performance. I will see you in the next session.